All right, we're starting a new chapter. Right now, this chapter is more on the applications of the derivative and interpreting the result that you get from the derivative. So, kind of picking up where we left off last week when we were talking about the relationship between position, velocity, speed, and acceleration. But this is going to be a little more abstract. So, first, I'm going to show you what the concepts are, and then we'll work through a couple of examples so you can sort of see how to solve this. Okay? So I'm just going to read the textbook along with you and explain and break things down where I think you may have some concerns. Okay. So, extrema. Extrema is essentially where you have a maximum or a minimum, right? So it says right here where I'm kind of jabbing, the minimum and maximum value of a function on an interval are the extreme values, or the extrema. The singular form of extrema is extremum, of the function on the interval. The minimum maximum of a function on an interval are also called the absolute minimum or the absolute maximum, or the global minimum, global maximum. All right. Extrema can occur at interior points or endpoints of an interval. Extrema that occur at the endpoints are called endpoint extremas. So that basic idea that you guys talked about and integrated to about the local max, local mins, this kind of comes back into play right now. Except now we're just talking about on a more global scale, like absolutely this is the highest point or the lowest point that this graph is going to produce. All right. And sometimes a function doesn't necessarily have a max or min within an interval. And that's, we have examples over here on the side that they mentioned in figure 3a, 3b. The important part is the extreme value theorem, and it's a very simple idea. So if f is a continuous function on an enclosed interval from a to b, then f has both a minimum and a maximum on that interval. All right. So if we look over here, example 1, we have the graph of x squared plus 1. If you notice, it's starting from -1 all the way to 2. That's the closed intervals. If you notice, they have closed circles right there at x equals -1 and x equals positive 2. So visually looking at the graph, we can see that we have some things we need to look at. Hopefully, can cooperate. So over here, and over here, right? Those 3 points that highlighted are points of interest. Now we have the graph. We can kind of see that where the highest point where the low points are. But we have to take into account the wording that they use. So they say closed interval, which means we're starting at exactly 1 point and we're ending at exactly 1 other point. If you look at part B, we have a continuous function, but it's not on a closed interval. So it definitely has a minimum because it has a single value. Technically, it doesn't have a single highest value, right? So here it's not included. We cannot count that as a maximum, so we cannot define what that would be. And if you guys try to think about the nature of real numbers, there's always 1.9. All right, what about 1.99? What about 1.999? And so forth. So that's why it's important that we have a closed interval. To talk about continuity, if we look at part C, well, where we thought the minimum point would be located doesn't exist. So that's why it's important that we have both continuity and that we have the closed interval, because those are the only two things we need to have to guarantee that these points will exist. Talking about the minimum or the maximum within an interval.